In this video, we're going to look at the steps involved to find the tangent and normal functions to a particular function f of x here. So in this case, f of x is defined as x cubed minus 3x squared minus x plus 3. And we're going to find the tangent and normal functions at x equals negative 0.5, 0.5, and finally 2.5. Now to do this, the first step involved is we first have to find the derivative, or I should say we first have to calculate the derivative of our function that we're trying to find the tangent and normal functions to. So in this case, f of x. So simply writing out f of x like so. Alright, now next step, need to take the derivative. Now I can go two ways. Either I can use first principles and go through the entire process of f of x plus h minus f of x all over h and then evaluate the limit as h approaches 0. Or I can simply use the simple power rule. So in this case I'm going to use the simple power rule because the question itself doesn't tell me which method to use. So simple power rule is obviously the easiest. So I'm going to do that. So simple power rule. Done. So our derivative f dash of x is equal to 3x squared take 6x minus 1. Now moving down, remembering that we do have a calculator that can sketch graphs, we're going to sketch the function f of x. So notice it's not f dash of x, but rather it is f of x. So to sketch this function, all I'm going to do is I'm going to draw a Cartesian plane. Now, when you're drawing your Cartesian plane, of course, you should always use a ruler so you get nice straight lines. But with Microsoft Word, I don't have that luxury, so I'm just going to have to make do with a freehand drawing. Now, if I sketch it on my calculator, the function comes out to look something like this. So, something like that. So it crosses the x-axis in 3 different points. Now, putting the roots in, we're going to get negative 1. Oops, let's get rid of that because I'm not doing signatures. Negative 1, 1, and finally 3. And the point at which it cuts this y-axis is at y equals 3, like so. Alright, so that should satisfy that question. Now, next part is it's asking us to calculate f dash of 0 or negative 0.5, 0.5, and 2.5. So, of course, to do these, we need to get our derivative function, so f dash of x. And we know f dash of x is equal to, let's go up, 3x squared minus 6x minus 1. Now, going for negative 0.5, we're going to get f dash of negative 0.5. And every time we see x, we have to replace it with negative 0.5, like so. And then using the calculator, we have to evaluate this. So getting the calculator on it, thus we end up with 2.75. 2.75. Then we get f dash of 0.5. And this one ends up to be, putting it in our calculator, it comes out to be negative 3.25. And then f dash of 2.5. This one turns out to be, the same as the first one, as 2.5. 2.75, like so. So remember, f dash of a number, this tells us the slope of the tangent, at the location x given here. Now going down, it's saying calculate the following and mark the points on your beautiful graph in part B. So f of negative 0.5, f of 0.5, and f of 2.5. So this one is f of, not f dash of. So f of in this case is going to be f of x is equal to x cubed. And then let's have a look up. X cubed minus 3x squared minus x plus 3. Minus x plus 3. Now substituting in negative 0.5, negative there, minus negative 0.5, then finally plus 3. So evaluating this with our calculators, it comes out to be 2.625. 2.625. So now doing the other two, we're going to get f of 0.5 equals and f of 2.5, and just quickly they're going to equal 1.875 like so, and then the other one is going to be negative 2, let's get rid of this, negative 2.625, negative 2.625 like so. And then the second part says mark it on your graph. Well, alright, finding negative half, it's going to be roughly there. So we're going to get negative 0.5, and when it's negative 0.5, it's 2.625. Like so. Then for 0.5, so somewhere around there, just notice my scale is absolutely atrocious. We're going to get 0.5, 1.875. And then finally for 2.5, well, it's going to be somewhere around there. So it will look something like 2.5 would be negative 2.625, like so. Alright, moving on. We've got it marked on our scale. Our next part is, now we endeavor to state the equation of the tangent of the 3 points of x listed at the top, remembering that y equals mx plus c, where m represents your gradient and c represents your y-intercept. State the values of m for each value of x. So this question, it sounds like we've got a bit of work to do, but in actuality, it's already done for us. Remember that the derivative tells us the slope of the original function for any value of x, and we've already calculated the slope of the at the values of x of the points we're interested in, so negative 0.5, 0.5, and 2.5. So the slope here, f dash of the number, it's actually the slope already calculated. So if m is equal to f dash of negative 0.5, then m itself, we've already calculated it to be 2.75, like so. So it's simply a case of identifying what it is we're working with. So that's negative 3.25, and this one is m equals 2.75. So yeah, too easy. Moving down, remembering that we can calculate the value of c, or the y-intercept, with the gradient and a point, because y equals mx plus c, we can rearrange it to c equals y minus mx. We've already got y and x because we've done the calculations over here. Now, if we want to arrange it in terms of the original function and the derivative, then it's f of x equals f dash of x times x plus c. And then we can rearrange to solve c as f of x minus f dash of x times x. So computing the values of c at or when x equals negative 0.5, it's simply a case of going c equals y minus mx, and that's the same as writing f of x minus f dash of x times x. And for, say, for example, negative 0.5, once again, we've already calculated those values. So we're simply going to sub in the values of f of x, f dash of x, and x for the value of negative 0.5 for x. So in this case, the gradient's 2.75. Actually, I'm ahead of myself. The value of y, or this vertical value for f of negative 0.5 is 2.625. Take, and the gradient is 2.75 times negative 0.5. Now, calculating this value using our calculators, we find that we get a nice convenient number of c equals 4. Now, going over to b, following the same process of y equals f of 0.5 minus f dash of 0.5 times that, actually yes, that, then substituting in the values, f for 0.5 is 1.875 minus f dash of 0.5 is negative 3.25 times 0.5, like so. Simply putting that in the calculator, we end up with the result c equals 3.5. Too easy. Then finally, for the last one of 2.5, repeating the process, we're going to get c equals f of 2.5 minus f dash of 2.5 times 2.5. Getting these values and throwing them in the calculator, we're going to end up with negative 9.5. Done. Alright, now putting it together, state the equations of the tangent to the curve at points x, so the x values that we've just been computing. So notice that we've got the values of m over here, and we've got the values of c. It's simply a case of putting it all together. So for let's say x equals negative 0.5, the equation is going to be y equals, and our gradient was 2.75 x plus 4. So the first one is done. For x equals 0.5, our gradient was negative 3.25. Y equals negative 3.25 x plus 3.5. So that's our value we'll see here. And then finally, for x equals 2.5, the value for the equation is, let's go up to see the gradient, 2.75 x minus 9.5, because it's minus 9.5 there. So there we go. We've got the equations of the tangent to the curve at points negative 0.5, 0.5, and 2.5. Now, having a look at what that actually looks like. Say, for example, we've got our graph here. So we've got in blue, this is our function. Now, having a look at the points, so the first one is a equals negative 0.5. So that's going to be over here. So indeed at the location negative 0.5 and 2.625. we'll turn that coordinate on, like so. So this is where our tangent is going to be at. And if we draw the tangent, so the gradient is indeed 2.75 and the y-intercept is at 4. Now if we go for the other ones, we go for say 0.5. Have a look. So it's at the location 0.5 and 1.875. So that's what we were expecting. And the gradient itself, so there's two elements. See if it will, it's not going to let us do it that way. The gradient is indeed negative 3.25 and the y-intercept is 3.5. And finally for 2.5, we're down here. So again, we're getting a positive gradient of 2.75 once more. It's got a y-intercept of negative 9.5. So y-intercept all the way down here at 9.5. And it touches at 2.5 and negative 2.625. So this is indeed the tangent there. Putting everything together, it's going to look like this. So this is the fruits of our labor, at least for the first part. Now, the second part is remembering that the normal to the tangent, remembering that the normal to the tangent to a line can be calculated as n equals 1 over negative 1 over m, or n equals negative 1 over f dash of x. So what we need to do is we need to recalculate the gradients we're looking for, and then obviously we need to recalculate our values of c from here. So repeating the process, we're going to get our first gradient was 2.75 for m equals 2.75. Then our normal is going to be negative 1 over 2.75, and that will come out to be something not very good. So we'll leave it as normal. In this case is negative 1 over 2.75, but it's going to be roughly 0.364. Now finding the y-intercept, we're going to get the values itself, they're still going to remain the same. So we're still going to use x equals negative 0.5, but then we're still going to use 2.625 here. So c is 2.625 times negative 1 over 2.75, and then multiply that with negative 0.5. So this expression on the right here will tell us the location of the y-intercept. Going up, let's have a look. Oops, my mistake. That should be a negative, like so. There we go. So 2.625. And it's going to roughly come out to be 2.443. Like so. So therefore the normal is described as y equals, and in this case roughly 0.364 x plus 2.443 Having a look at what that would look like in Desmos. So shrink that down a little, and we'll go for where can we put it? We will put it here, y equals nx plus, in this case we'll go b, and our value for n is going to be negative 1 over 2.75 and therefore our b is going to be at 2.443, like so. And lo and behold, as we can see, this red line cuts the green line at exactly 90 degrees, so therefore this is the correct calculation for the normal to the tangent at negative 0.5. Now if we follow the same process, and let's just change that color, it's a little bit nicer. Yeah, purple. That'll work. So we need to find the normal to the other two as well. So if we recall the gradient for negative or positive 0.5 is negative 3.25. Negative 0.5, and is going to equal negative minus 3.25 over 1. Let's just double check. Yeah, negative, like so, and then of course the two negatives are going to cancel out, so it simply becomes 3.25. So 1 over 3.25, like so. Now finding the y-intercept. We're going to get c equals, and we have to look for the value f of x at that location, and it is 1.875. 1.875 minus 1 over 3.25 times 0.5. Now if I throw this in my calculator, 1.721, 1.721, like so. So therefore our normal at x equals 0.5 is simply equal to y equals the gradient 1 over 3.25 x plus 1.721, throwing it in Desmos once again. Let's write this as a list. So 1.721 and that needs to be a comma. So therefore the normal here cuts through the tangent at 90 degrees, and normal over here, so this point here, cuts through our tangent at 90 degrees as well. So the calculation seems to be correct. Now we need to just find this normal, and then we are done and dusted with this question. So jumping into it, we're going to get, so move this over. Perfect. Now jumping into it for x equals 2.5 n is going to be, it was -1 over 2.75, and that's roughly equal to 0.364, like so. So the gradient, it was the same as the first one, so we can just reuse that calculation. Now finding the y-intercept, we're going to find that it is, well, the value of y for f of x at 2.5 is -2.625. And then it's going to be take 1 over 2.75. That should be a negative, so should this one. So take minus times 2.5. I'm putting that in our calculators. It comes out to be -1.716, and therefore the normal at x equals 2.5 comes out to be y equals -1 over 2.75, and then that's going to be x minus 1.716. Alright, flipping back. So we're going to use the same gradient once again. And then -1.716. And lo and behold, the new function that's been graphed is perpendicular to the tangent at 2.5 and -2.625. And on top of that, it cuts through the common point as well. So this has been a video on how to do this new question here that goes through the steps of finding the tangent and the normal functions to an original function, so a nonlinear original function listed up here at the points stated over here as well. So a little bit long, but we got there in the end.